groups or totally different companies. So there's no guarantee that the most fitting camera is being used for the right algorithm. So the overarching question I'm trying to address today is how do we design the best camera for specific computer vision applications? And we can measure what best means in terms of task-specific accuracy, speed, energy efficiency, and other metrics. Here's a quick outline of what I'm going to be talking about. I'll give some background into Fourier optics and optical encoding, which is how we'll approach this problem. And then I'll talk about a couple of projects that highlight different ways we can try to tackle this overarching problem, including heuristic design, and then this concept of deep optics, where we actually optimize the camera with the algorithms. So all of this research falls under the broader umbrella of computational imaging, which refers to this co-design of optics, sensors, and algorithms. Computational imaging, you're probably familiar with on some level. It's been used to produce applications such as HDR, panorama, portrait mode, or more recently, you may have heard about imaging a black hole. There's a lot of different ways we can go about this computational imaging type of process, but one thing we're going to use, the framework we're going to use, is to consider imaging as a linear space invariant system. If you took any signals and systems class, you may be familiar with this idea of linear time invariant systems, where you have some system, black box system, that can perform some sort of transformation on an input signal, and we can analyze this in either the primal domain or the Fourier domain. So with our image processing, instead of a 1D signal, we have a 2D image, and the Fourier domain is simply the 2D Fourier transform of that image. Our system can be characterized by a point spread function, or the Fourier transform of which is an optical transfer function, and that's essentially this 2D impulse response that describes how a point in space spreads out on your camera sensor. In this case, this example, we're looking at a low-pass filter. So the OTF is describing how different frequencies are being passed through the system. The center part of that square representation encapsulates the lower frequencies, whereas the edges of that square are where the higher frequencies are. So in this case, the white region is allowing the low frequencies to pass, while the black area is blocking the higher frequency information. So the output of this, if you're familiar with signal processing on some level, is going to be a blurred version of the input signal. So here is just looking like a blurry version of the input image. As another example, if we have a high-pass filter, we would kind of reverse the colors in that OTF. So now we're allowing the high frequency information to pass through, blocking the lower frequency information, and as you might expect, we now have only the sharp information of that image, which just has the edges of those pairs. And the way we get from the input image to the output image is either a convolution in the primal domain, so convolving the input image with the Psf, or multiplying the Fourier representation with the OTF. What's unique about computational imaging is that we can actually design imaging hardware to encapsulate different Psfs and OTFs. So by customizing things like lenses, filters, apertures, we can design a camera that can produce the desired output image. We'll use this concept of Fourier optics to more carefully understand this. So in Fourier optics, we're able to decompose any input light waveform into a spectrum of angular plane waves. So essentially, whatever light form we have, we can decompose that, described in that equation, as a summation of plane waves, so these angular plane waves traveling at different angles. If you're familiar with Fourier transforms, you can notice that this already starts to look like a Fourier transform. And indeed, we have this idea that an ideal thin lens can perform a Fourier transform at one focal length away. So basically, if you have a lens placed in front of an image that's coherent, then one focal length away from that lens, you'll get the Fourier transform of that image. There's still a little disconnect here. How do these angles relate to the frequencies that we just talked about? This is a little bit hand-wavy, but we can consider these two plane waves that are coming in at two different angles, one at a larger angle and one at a smaller angle. We're going to intersect both of these with an intersecting plane and look at where the peaks of those waves intersect with that plane. So if you just consider the spatial frequency of those points, you see that a larger angle is related to a higher spatial frequency, whereas a smaller angle is related to a lower spatial frequency. So this is how we can relate the physical wave with the actual spatial frequency of an image. Now, putting all those concepts together, we can actually create a filtering system in optics. So here I'm just showing a 4 focal length system, or a 4F system, where we're essentially performing a Fourier transform for this first lens, applying some sort of filter here, and then performing an inverse Fourier transform with the second lens. So if we come back to the example shown earlier, if I input the image of a parrot on that projecting screen, the DMD, and I just place an open aperture at the Fourier plane, then you get the same output image on the right, just flipped over due to optics. Now if we close in that aperture, we're causing that low bandpass filtering, and now we get a blurry version of the image. Now I just have to complicate this a little bit more. So not all life happens at the focal plane. Whenever you take an image of a scene, there's usually objects that are in focus and out of focus. And we know instinctively that these different planes are convolved with different point square functions. For example, if you take an image of something where something is up close and something is far away, and you're focusing on the close object, you'll notice that parts of the image are blurrier. And this is because different parts of that image are convolved with different point spread functions. So for example, the image in the region in the red may be convolved with this point spread function highlighted here, whereas the farther away plane is convolved with the larger point spread function, which causes that depth-dependent convolution and the blurring effects that we see in imaging. Now that we understand all of this, the way that we can model a 3D imaging system, we're able to actually manipulate the elements to encode certain information by designing more exotic PSFs. I'm going to show a couple examples of these. The cubic phase mask is a different type of kind of custom lens that has this thickness profile, and it produces very strange looking PSFs on the right. And the advantage of these PSFs is that they remain very similar over a larger depth of field. So with some image processing, you're able to get a final image that has a larger depth of field. Another example is a coded aperture for depth estimation. In this, we're using a binary amplitude mask placed in the center of the camera, and this has been shown to be better for depth estimation. And for those of you who come from a biology background, you may be aware of this double helix point spread function for super resolution. And in this case, the depth of your fluorescent emitter is encoded in the rotation of those 2 points, and that's how we can encode super resolution depth information into our image. All of these examples are showing how custom PSFs can be engineered for specific imaging applications, and this is an idea that we're going to take advantage of throughout all of the projects that I'll discuss now. All right, so coming back to this overarching question of how do we design cameras for specific applications, we're going to look at 2 main approaches. The first I'll talk about is what I'll refer to as heuristic design, where once we have an application, we come up with certain metrics that can predict how well an optical design is going to perform. And then we'll move on to deep optics, which I'll get more into later. So for heuristic design, the project that I'm going to talk about is Aperture Interference light field microscopy. Light field microscopy is a method of volumetric imaging in fluorescence microscopy, where once we add these lenslets into the microscope, we're able to multiplex all the 3D information into a single snapshot. So as compared to things like confocal, where you have to scan a volume point by point, or light sheet, where you have to take one image after the other, with a light field microscope, you take a single snapshot, allowing for a full 3D volume reconstruction. So this seems to be a really good advantage, allowing us to image processes that are happening really quickly in biology, but there is a disadvantage. LFM, or light field microscopy, does suffer from poor spatial resolution. If you compare these 2 videos, which are both videos of calcium imaging in zebrafish, you can see the light sheet video on the left has a much better resolution than the light field video on the right. Our goal here is to understand why does light field microscopy suffer from this lower spatial resolution, and how can we improve it? This brings us to the main implementations of light field microscopy. So on the left is the lenslet array approach that we mentioned in the previous slides. In the middle, you can also use a camera array to multiple cameras to capture that same information. Or you could also use an aperture mask that you scan across the aperture to sequentially capture that information. So although with the aperture mask approach, we no longer have that single snapshot advantage, it provides a really convenient way to study this fundamental resolution limit so that we can further improve upon it. So we're going to take that aperture mask approach, introduce this idea of aperture interference, and see how that can improve our spatial resolution. Again, we're going to be using Fourier optics, what we discussed earlier, to analyze the LFM different scanning sequences. So on the left, I'm showing here a microscope diagram. We can relate the different parts of the microscope to the same kinds of primal and Fourier domains that I talked about earlier. So at the object plane, you're in your primal domain, and that's where you'll have your sample. Then the objective essentially takes a Fourier transform, and at the back of the objective, we can place some sort of aperture mask, like the one I showed earlier, and this is now going to be in the Fourier domain. And the types of aperture mask sequences are like shown here. And then next, we have a tube lens in our microscope that takes one more Fourier transform that brings us back to the primal domain, and that's where we would put a camera to capture the final image. Right, so now we're going to dive more into this analysis and look at how the PSFs and OTFs look for these different sampling strategies. First, we're going to show a single pinhole sampling scheme, which is reflective of conventional light field microscopy. And this is just going to involve a single pinhole moving across the aperture. And then if you look at the bottom, we have a couple different ways to kind of analyze how this is performing. So on the left is going to be the point spread function. And now this point spread function is in depth. So basically, as you start in the middle of the image, that's going to be the focal plane. And as you move away, that's how the PSF spreads out in space. And because we're coming in at different angles at the aperture plane, you'll see how that changes. So in the next image over, that's showing the OTF, or the Fourier transform of the PSF, for each of those individual PSFs. What's more important here is to look at the combined OTF, which is going to stack all of those individual OTFs together to look at the total frequency coverage of the system. And what we're trying to achieve here is to fill in this white outlined region, which is essentially the upper bound of the information that we can have due to the objective itself. The takeaway here is that with a conventional light field sampling scheme, only the low spatial frequencies in the center of that region are allowed through, and this is what results in the poor spatial resolution. Now we introduced this idea of aperture interference, where we're going to open up multiple pinholes, and now let's look at the effect of that. So with this type of sampling scheme, we're actually able to pretty much fill up all of that outlined white region, which is indicative of the higher resolution that this strategy may be able to yield. From this insight, we're going to design a couple of sampling schemes in 2D. So instead of just looking at X and Z, we now have X, Y, and Z. So for the conventional LF pinhole approach, we just have these little pinholes that move across our aperture. We propose this idea called ALF circles, which includes pinholes that move around, but now they're also changing sizes. And you can see from the OTF plot that now this is covering a much larger region than the previous one. And finally, we also want to test this idea of ALF rings, where instead of circles, we have rings for certain reasons that I'm not going to get into here. Okay, so once we have those proposed designs, we're going to test these in simulation. I'm just going to show here very simple results. These are coming from a simulation of a test resolution chart volume where we have resolution chart bars that are stacked in space. And our goal is to reconstruct all of these bars so that we can see the spaces between those lines. I'm going to show the reconstructions in this type of format. So these are maximum intensity projections. And you can imagine them as looking down at a volume from the top, from the side, and from the other side. Here are the results of that. Starting from the left, we have LF pinholes then ALF circles, and then ALF rings. And the most important part here is the area outlined in blue. And if I zoom in here, you can see that LF pinholes has a very poor spatial resolution. ALF circles does better at the focal plane, and then ALF rings does even better throughout the volume. So this is a good sign so far. Our simulations are working. Our new aperture interference strategies are yielding a higher resolution. So we move on to our actual experimental setup where we build up this in a microscope, and we print these little aperture masks that we're going to physically place inside at plane number 3 in that image. Now I'll go through the experimental results from those same resolution charts. So here I have a planar resolution chart, and I'm just moving it away from the focal plane. So z equals 0 is at the focal plane, and then these move farther and farther away. You can pay most attention to the little zoomed in areas at the right, and for LF pinholes, we see that we have very poor spatial resolution, just as we did in the simulations. With ALF circles, we're able to get a better resolution at the focal plane, but then this drops off quickly after that. And finally, with ALF rings, we get the higher resolution over an extended depth of field. So all of this just supports the same trends we saw in the simulations. All right, so we did some other experiments, but I'll just give you the main conclusions here. Using our Fourier optics analysis, we're able to understand the resolution limits of conventional light field, and we analyze the resolution limits of alternative sampling schemes. We're able to formulate certain heuristics that help us predict the performance of different sampling strategies. And we show in both simulations and physical experiments that our proposed strategies are yielding a higher resolution. But something about this didn't feel quite complete. We proposed these different mask designs, but it wasn't quite clear whether they were the best designs. So basically, using the heuristics, we could try to think of very specifically how we could try to improve those heuristics, but we didn't fully formally optimize the entire system. So this leads us to our second approach of deep optics, where now we're going to take advantage of the deep learning framework to try to optimize the entire system end to end. All right, so in the past 10 years, a lot of progress has been made in research into neural networks, and they've been useful for things like image classification, object detection, and even generating new faces. So on some level, we can think of a neural network as a brain made up of many layers of interconnected mathematical neurons. And if we train this network on something like image classification, then maybe we feed in some image that looks like this. It goes through a sequence of layers and filters, and finally it produces some output bird. So while this research has been very heavily studied in computer vision labs, it's often not paid attention to where this image actually came from. So what is the imaging hardware that actually produced that image, and could there have been a better image to start off with? So this is what we focus on. We're bringing the camera into this loop so that we can fully consider the system and make it more applicable to real-world situations. And once we include the camera, we can optimize things like lenses, filters, apertures, and other things in a full end-to-end manner. We're going to look at two different angles to this idea of deep optics. First, we'll consider optical computing as a replacement for electronic computing. So say you have some network that has 5 layers. If you have some energy constraints or some time constraints, we can try to replace one of those layers with an optical layer that can work faster because it's happening at the speed of light and with possibly lower energy consumption, since optics is a little bit better at parallel processing. The other angle we'll look at is to use optical computing as a supplement for electronic computing. So if you didn't have any concerns with power consumption or time, we could focus the optics on doing something that the electronics cannot do. So here, maybe you still have those 5 layers, but you're adding another optical layer to give you extra task-specific performance benefits. So for part A, we're going to look into deep optics for image classification. A traditional convolutional neural network for image classification may look something like this. You have an input image, it goes through a sequence of convolutional layers, maybe some fully connected layers, and at the output you get a vector of scores, where each element of that vector corresponds to how much you're predicting that image to be in each class. we're going to focus on this first convolutional layer here and see whether we can use optics to perform the same computations as this standard convolutional layer. And this is one step towards this idea of an optical neural network, where we can maybe do all of this in optics. We're going to return back to this 4F system that I showed you earlier. So again, we want to take advantage of the convolutions that occur in optics and design certain PSFs that can now perform the whole convolutional layer of a standard neural network. So at the bottom left, that's how a standard convolutional layer might look. We have your input image, a stack of convolutional kernels, and you get a stack in your output volume. With our optical convolutional layer, we're going to instead tile these kernels in a 2D array, and then the output will be the convolution of the input with this entire larger PSF. So ideally, we have the same information here as we do in the output volume on the left, and that would allow us to fully replace the standard convolutional layer. We want to make sure that this works, so we test this in the easiest way possible, a single layer neural network, or basically just a correlator. The model of this is shown here. In blue is basically just the 4F system, the optical convolutional layer. We read out the sensor image. We cut that sensor image up into different subregions corresponding to how many classes that we're looking at. We pick the brightest pixel from each of those regions, and then that gives us the class score for each of our different categories. So in this case, we're taking the highest class score to predict camera. In this example, we're looking at this type of data set where we have drawings of different classes such as rainbows, eyes, apples, and so on. We're going to build this up in a TensorFlow framework and then train it in a couple different steps. So first we have our Psf optimization. We're going to find the best Psf for that convolutional layer. And then second is going to be phase mask optimization, where we actually design, optimize for a phase mask, so the physical element that can produce that Psf. Out of the Psf optimization, we get some things that look like this. As you move from left to right, I'm adding in more and more constraints that make this more physically realizable Psf. The main takeaway here is that if we look at the accuracy at the top, we are able to maintain approximately the same accuracy, a little bit of a minor drop-off, but the same type of behavior is still evident in all of these kernels. So in all of these cases, you're seeing some sort of average shape of each of the categories, and this is what you would expect from a correlator. Now we're going to take this final Psf here, feed it into our phase mask optimization, and we get a phase mask that looks like this. So this is just the height profile of that lens. You can't really tell by eye what that really means, but if you take the Fourier transform of that, then you actually get a Psf that looks like this, which actually very closely matches this target Psf. And now if we input an image that looks like the ice cream cone, the output image looks something like this, and if we grab the brightest pixel, it corresponds to the class of ice cream. So this is what we want. Now that we've shown that it seems to work well for a single layer case, we want to extend it a little bit more to a more complex system. And so we bring in a second electronic layer to build up this optoelectronic 2-layer CNN. Now our model has changed a little bit to look like this. We have our same optical convolutional layer, but now when we feed it into our electronic computing, instead of directly reading out the scores, we pass the cropped images into a second fully connected layer just to give the system a little bit more power, processing capability, and then we read the class scores from the end. We're able to switch now to a more difficult data set since we have 2 layers instead of 1. And we do pretty much the same type of training process with now an extra end-to-end refinement added in. Great. So first off, we had the Psf optimization. So now for the 2-layer CNN, the types of Psfs we get look like this, and you can see those typical edge filter kernels that you normally do see in a convolutional neural network. Once we have the target Psf, we move on to phase mask optimization, get something like this. For this one, we're actually going to make a physical prototype. So we go ahead and fabricate that mask. It's shown on the bottom left, and here I'm just showing, here this just shows the pattern a little bit more in that mask template. You can see how the different kernel information is kind of encoded there it's not very intuitive, but it's there. So if you compare the first layer, the first row and the second row here, you can see that the two images actually look pretty similar, which suggests that our fabrication went well. And to test this out, we built up our actual ONN optical neural network prototype, which looks something like this. Here again is that same 4F system, just top view, and then we place our fabricated mask right in the middle there at the 4/8 plane. This is showing some of our experimental images. The top row is all simulated, and the second row are the captured images. So what we want is our capture to match this as well as possible, and you can see that they do resemble each other very closely. I'm going to move on to our quantitative results here. I'm going to go through this table line row by row so that you can get a sense of where our advantages lie. So starting with our first row, these are the results from a single fully connected network. So basically just one layer. This is going to be the low baseline for performance. That's why it's highlighted in red. But it also is going to have a very low computational cost. Now if we want to improve the performance electronically, we add in a standard convolutional layer, and now the test accuracy goes up to about 50%. Unfortunately, we do also increase the computational cost, so the flop count, by a lot. With our optical convolutional layer, we're able to maintain that test accuracy, but bring that flop count back down. So this is the main contribution of our optical convolutional layer. We're able to gain accuracy without increasing the computational cost as much as with a standard electronic layer. And then finally, these are the experimental numbers. So of course, with experiments, the numbers goes down a little bit, but our flop count is still low, and we're still able to achieve a higher accuracy than with a single fully connected layer. And the bottom is just showing some examples there. Okay, so from this project, we make a couple of conclusions. First, we have proposed this design of an optimizable optical convolutional layer with tiled instead of stacked kernels. We validated the performance of this optical convolutional layer first in a very simple single layer network. Then we connected this to an electronic fully connected layer so that we have a hybrid system. And then we showed how that can improve the performance with minimal additional computational costs. Finally, we built up this experimental prototype and showed that we could achieve experimental results on par with the simulated results. So now I'm going to switch to case B, where we're going to shift our gears a little bit and think of optical computing as a supplement for electronic computing. And the task that we're going to choose here is to look at deep optics for 3D vision. All right. So depth understanding is very important for many computer vision applications, including navigation, tracking, scene understanding, and so on. There's a couple of different existing methods for depth measurement today, but they all have their downsides, ranging from really high cost, high power requirements, or bulky form factors. Furthermore, all of these techniques are often connected with an RGB camera to supplement the depth information. So if we could just use the RGB camera by itself to estimate depth, that would be ideal. Unfortunately, monocular depth estimation, so depth estimation from a single image, does remain a challenge. And this is mostly due to the fact that depth information is lost with all-in-focus capture. So if we look at this camera projection diagram on the right, and we focus on this red pixel, once we use camera geometry to project that pixel back out into 3D space, it's unclear where on this red line that point actually came from. So that's how the depth information gets lost. Intuitively, we know as humans, though, that if we look at a single image, we are actually able to figure out what the depth would be. For example, if we look at this image, we all can kind of guess that this area is farther away than this area. And this is because we can use perspective, shading, and other types of contextual cues to guess what the depth is, and algorithms have been designed to use those cues to predict the depth. Unfortunately, those can also be tricked with using things like forced perspective, and that's why some of the more traditional monocular depth estimation methods have been insufficient. More recently, deep learning has been used to learn features instead of using handcrafted features, and this is thanks to the really large data sets that we have now to use for training neural networks. These are still not totally robust though. If we now input an image like this instead of a road, the networks may not have enough information to transfer that knowledge into this image. What we propose to do is to use optical cues to complement pictorial cues. If you consider this focal stack, where I'm shifting the focus of the camera from near to far, you see different things come into focus. And based on our experience, we know that these things that are in focus correspond to where the focal plane is. So with our framework of deep optics, we want to see whether we can use this to learn both optical and contextual cues to improve monocular depth estimation. To do this, of course, we have to have some sort of optical model that we can build into our full network, and so this is just the very simple model we use. We have points that are some distance away from a lens, and that's some distance away from your sensor. Basically, we have all of the equations that we need to calculate how this point would look on the sensor. Maybe it looks something like this. And another point would go through the same process, just with a different depth variable, and maybe look something like this. In 2D, those PSFs end up looking as shown. And you can see that the PSFs generally are blurrier out of focus, they sharpen up in focus, and then they blur out again away from the focal plane. These are all for a single wavelength. We can also model multiple wavelengths. So here's an example of that. We bring in 2 other wavelengths now, and because different wavelengths cannot be focused at the exact same plane with a single lens, it results in some chromatic aberrations like these. And you can actually get a sense of, at this point, how this optical information may be able to encode depth into our image. Up until this point, we hadn't really seen how the phase mask went into this, but we can also modify the phase mask that's to the left of the lens to come up with more exotic looking PSFs like these. Right. So once we have the PSFs, we want to actually use these to simulate our sensor images. So we have this depth-dependent convolution process here. And then once we have the simulated sensor image, we feed that into some neural network. In this case, we're using a UNet, and then use that to predict a depth map. We use the predicted depth map to calculate a loss with the ground truth depth map, and then that is used to update the lens parameters and the UNet weights, and this process continues for a certain number of iterations. Before we get into the optimized element, I'm going to show some examples of just a fixed lens and only optimizing the UNet to give you a sense of what optical encoding can do. So here I'm showing some results for a very simple data set, just white rectangles on a black background, and these rectangles are placed at different depths. If we use a camera that does all-in-focus capture, which is the typical type of capture that computer vision data sets use, then basically no depth information is encoded in these images, and they all look the same. The network, as a result, predicts the same depth for every single rectangle. And in these plots, on the x-axis, it corresponds to the left to right of those squares, and on the y-axis is the predicted depth, so they're all the same. If we add in defocus blur, now we have some optical information encoded that's encoding depth, and we see there is slightly better performance, but there's still this ambiguity of whether something is in front of or behind the focal plane. Finally, if we add in chromatic aberration, it actually resolves this depth ambiguity, and we get much better performance. So these are some ways in which optical encoding can preserve depth information, and now we're going to move on to looking at the actual optimized results. I'm going to go through this table row by row again, and you can pay attention to the graphs that pop up at the bottom. So starting with all in focus, and we're looking at the error in the depth estimation for a couple different data sets. With all in focus, we have the highest error. When we add in defocus and astigmatism, which are standard optical blurs, then our error decreases. When we add in chromatic aberration, it gets even better. And then finally, when we optimize a freeform lens, we get the best results, so the lowest error. So this is basically what we wanted to show from the very beginning. We wanted to be able to use our deep optics framework to find that depth estimation can be improved when we're optimizing the optical element along with the rest of the depth estimation network. And across all the different data sets, this seems to be the case. Now that you have that in mind, we'll look at some qualitative results just so you can convince yourself that that's true. So here, in each row is a different example, and from left to right, I'm showing the original image, the ground truth depth map, the all-in-focus depth map, which has a lot of errors, and then as you move right, you see fewer and fewer errors. Here are some other examples of that. And we can also compare our results to results from state-of-the-art literature. The different columns are just different error metrics, and the 3 rows here are different main methods from literature. I'm going to add in our results here. I highlighted all the best performing metrics in blue. So you can see that almost all across the board, our optimized lens is actually giving the best performance, even when compared to these really complicated networks that are specifically designed for depth estimation. We're only using a simple UNet in our depth estimation, so it'll be really interesting in the future to see how, if we can combine our optimizable optical element with a state-of-the-art neural network, what kind of results we can get. Here are some of the results from the other data set. They look like this, and then this is the example of the optimized PSFs. Here I'm just showing a video of the estimated depth, so you can get a sense of the temporal consistency. From our simulations on depth estimation, we're going to move on to our experiments. We make an optical prototype, but we're just going to use a lens with chromatic aberration instead of actually fabricating the fully optimizable lens, since in the previous project we already showed we can do that. What I need to do here is to calibrate the PSFs from our simulations with the actual PSFs of the camera, and then retrain the depth estimation network for that specific camera. Here are some of the experimental results from the optical prototype. I'm going to compare the all-in-focus captured image with the same image using chromatic aberration. So these are images that we actually took. If we look at these 2 parts of the image, you can see how the chromatic aberration image looks very different than the all-in-focus image, and somehow these chromatic aberrations on the edges of the letters are capturing the depth information. These are the depth maps that come out of that. And you can see that with chromatic aberration, we get a much better depth map. I'm going to show some more examples here. The top row are our captured images. The middle row are the estimated depth. And the bottom row is the estimated depth when we don't use chromatic aberration. So pretty consistently, across all these images, we're showing that when we have chromatic aberration in the image, we're able to reconstruct a much better depth map out of that image. At this point, we can make a couple of conclusions. We built this optical image formation model that we integrated with a neural network for depth estimation. We tested this with a couple of different lens settings and different data sets, and we've showed that the optimized freeform mask yields the best results, and chromatic aberration came in a close second. We confirmed as well that our chromatic aberrations do work better than all-in-focus images in real-world results. But there is a question that we're still left with that we were slightly concerned about. So now we have a bunch of blurry images, and it could be possible that in these blurry images, we preserve depth information, but we sacrificed other useful information. We want to address this concern. We decided to test whether our optimized depth estimation lens could also perform well at a higher level 3D vision task. And for this, we're going to choose the task of 3D object detection. This is something that's useful for things like autonomous driving, interacting with virtual reality environments, or things like robotic surgery, or robotic sandwich making. We decided to choose 3D object detection because I noticed this really large gap between monocular 3D estimation performance and 3D object detection performance when LiDAR information or ground truth depth information was present. So if we're able to use our monocular images to predict a better depth map, then perhaps we could get somewhere in between these. Our approach here is to use one of the best strategies for object detection and customize it for RGB only input. So this is what frustum point nets looks like, or f point net. It takes in an RGB image and ground truth depth. It predicts 2D bounding boxes on that RGB image, projects those 2D boxes into a 3D frustum, uses a point cloud instance segmentation to find which points in your point cloud belong to an object, and then finally it forms a bounding box around that object and predicts a class category. To adapt this, all we do is instead of using the ground truth depth, we're going to feed in the predicted depth. And for these experiments, we're going to test the difference between an all-in-focus and an optimized lens. So first thing, we're going to look at the 2D object detection part of the network. We just do 2D detection with a standard framework, standard network, and here are the results from that. So it turns out that our all-in-focus image and optimized image perform really well, or perform really similarly in this 2D object detection task. This is a good sign because initially I was concerned that the 2D object detection would suffer in our chromatic aberration image because these images are blurrier. But because these two are still performing pretty much on par, this is a good sign to continue with the 3D object detection. Here's what the 2D object detection looks like. Basically, they look the same. So now that we have this part done, we move on to training the next part. We use standard approaches to train this. And finally, I'm going to show the results here. So coming back to this table, again, remember that the monocular performance was very poor, and the performance with the ground truth depth information was much better. When we add on our results, we are able to achieve some sort of performance that is right in between these two. And what's also important to notice is that all of our results from the optimized lens outperform the all-in-focus lens. For completeness, I'm also adding the other two categories. And again, the optimized lens always performs better than the all-in-focus lens. All right. And then here's just a video of what those object detection boxes look like. It's a little bit hard to see in the video, but it's going to stop at the end, and we can look at the last frame. So if you look at the black car on the left, middle left of this image, then you can see how the optimized image is able to get a much tighter bounding box around that car than the all-in-focus image, and that's the kind of improvement that results in the better performance. Cool. So coming back to our conclusions, we already discussed the first four. And now, because we've done our experiments with 3D object detection, we've shown that the improved depth estimation also carries over to higher level 3D vision. Just to summarize here, this is what we're able to do with our deep optics framework. All right. Now just summarize everything I talked about. So we had this question of how do we design cameras to best suit a specific application. We started with this approach of heuristic design, where it was a very kind of manual process, where we would come up with a design, evaluate it with certain heuristics, go back to another design, evaluate it with the same heuristics, and compare them like so. But this was difficult to actually settle upon what the best solution would be, so we moved into this approach called deep optics. And here we were able to connect the actual optical design with the image processing pipeline and train them together to find the best result. We looked at two different strategies for doing this, one in which optical computing acted as a replacement, and the other in which optical computing acted as a supplement, and both of those showed different types of benefits. And generally, as the amount of objects in our lives that are becoming smarter and smarter continues to increase, the potential for deep optics is also continuing to grow, and hopefully in the future we'll see more intelligently designed systems in which the camera is more customized for its application. Here are some of the other projects I worked on. The ones in blue I didn't talk about in this presentation. And that wraps it up. So I can take some questions, and then I'll thank some people.
Okay, so we're going to do questions from the general audience?
Yeah, my question is
more of a thought experiment, but could your system give accurate depths for a picture environment versus an actual environment? And if not, what do you think are the steps needed to get there, aside from using something like LiDAR?
A picture environment?
Yeah, like a picture. If you take a picture of this room versus you actually have your camera display.
Yeah, that's a pretty different situation because the camera that's taking the picture is going to be different than the camera that was optimized with the system. So there would not be as much as an advantage of connecting two different, like taking a picture of a picture, basically. But if you place the camera in this room and you kind of included that in the full optimization process, then that I think would be a situation where you could improve.
In the first part of your talk, the heuristic approach, I didn't understand how you went from the finding where you have like two apertures and you're moving them to the ring. Could you explain?
Oh yeah, so that was a heuristic that I didn't talk about. Let me show you. So I only really mentioned the frequency space coverage, but there's another thing that has to do with invertibility. And here with the circles, all of these are overlapping. So in a way, it's like hard to disentangle or invert the forward model. Whereas for the rings, each of those is a sharper slice through your through the OTF, and that helps with the reconstruction process. And you can kind of think of it as each of the rings gives you a larger depth of field versus the circle, these circles. And that depth of field is what allows us to get the higher resolution over the extended depth of field.
So for the thematic activation approach to like depth perception, is there anything to be gained by kind of looking at a wider range of wavelengths? Like if you're, for example, including infrared and ultraviolet, would that give you a better?
Yeah, I think so. So we only tested 3 wavelengths corresponding to an RGB sensor, but there's lots of different approaches for hyperspectral imaging, where you actually look at a more like a higher resolution of wavelength information. And if we had a phase mask that cared about each of those different wavelengths, then perhaps you could get even better information, maybe for other applications too.
Do you have any sense for, so you do the cool validation at the end for the final project where you show that you can still do the 3D object recognition very well. Did you ever look into, if you just deconvolve out the aberrated point spread function, like how good of a image you can recover?
I didn't look at that, but I considered it, and to do that while training the depth estimation network, instead of just calculating the loss on the depth map, I can also calculate the depth on the reconstructed image, so it would be both an autoencoder and a depth map estimation. So I think that's something that you could do.
What's the next thing that you've opted? What's the next challenge you want to work on?
There's a lot of different applications. Obviously, you can just kind of pick any computer vision application and see if you can find a better lens for it. There are a lot of systems now that are incorporating multiple cameras, so one thing to do could be to see if we had 2 cameras, how could 2 different lenses be optimized to work well together to produce even better outputs.
So in the case of multiple cameras, when you're training, I guess now you're going to have some algorithm or antagonism or logic between the 2 models.
So I think it could be fairly straightforward, at least in the first pass, where, so here we basically just feed in one sensor image, but you could replicate this into 2 branches, feed those in together to your network and see what that can give you. It's kind of like 2 channels. Well, we have RGB, but maybe now you have 2R, 2G, and 2B.
Okay, if there are no more questions, then we'll take a quick break, and that concludes the public session.
Oh wait, yeah, Gordon did tell me he didn't want me to spend much time on the acknowledgements, but maybe just a few minutes. So Al, thanks for coming and serving as the chair. I think you do a lot of really cool research that applies these types of computational imaging techniques to medical situations. Jin, thanks for coming as well. I really enjoyed one of the first classes I took on imaging in bioengineering that introduced me to so many different imaging applications. Marcus, you were there on the first day of so many of our days at Stanford, and your class really solidified us, and I enjoyed your guidance through quals and through this. Doug, thanks for being here on last minute notice. I appreciate that a lot. Yeah. And Gordon, of course, thanks for being such a great advisor. I think there's a lot of things I take for granted, like you always reply to emails, you always make time to meet with us, and all your suggestions make sense. So yeah, thanks to all of you guys for being here. And then of course our lab group, it's been really fun working with all of you guys over the past 5 years. Mark and Evan are newer members, but they helped me a lot in this most recent project. Isaac, he was the first person I worked with in the group, and at first he was really intimidating to me, but now, since then I've become one of his housemates as well, and it's been fun educating him on Nicki Minaj lyrics. And the other people in the group that I've sat with for the past 5 years, Hayato, Nitish, Robert, David, and Vincent, I'm really glad you guys were there as my lab mates. I learned so much from Vincent on deep learning, and I learned so much from Nitish on M-dashes and N-dashes. Yeah. So we had a lot of fun times. This was the hike we went on one time where we almost lost a member, and he is indeed not here today. This whole SCI gear kind of progress. It took a really long time, but we were finally able to make t-shirts, and maybe that's representative of my PhD. And then, of course, I can't forget this time we went wine tasting, and it was the one time that Hayato did not have to drive himself home. This is I also want to acknowledge the BioE cohort that was with me in the first couple years of this PhD. We had a lot of fun times together doing P-sets or doing other things. We all graduated with our masters here in this photo, and hopefully some of you guys will join me, or hopefully I'll be there. I want to thank all my friends for making life fun outside of school, and of course, this person who is a person of many talents, including pickling jalapenos, braiding my hair, being an Instagram boyfriend, evidenced by the many repeat photos, and asking important questions like, can I scramble eggs inside the shell? But yeah, he's been so supportive over the past 5 years, and I hope to continue supporting him for his PhD as well. And then finally, I want to thank my family for always being there.